Earlier, when we talked about Sturm-Liouville problems, I mentioned that they can become singular if either the p function has a zero somewhere in the domain of the problem that you're looking at, and we just saw an example of that, or if the interval for the independent variable is unbounded. So we're going to look at an example of that now. And so the spectrum consists of all the values for which L minus that value times the identity operator is non-invertible, right? And for regular Sturm-Liouville problems, it turns out one of the things that I mentioned earlier was that the eigenvalues are all discrete values, which maybe didn't make a whole lot of sense. But as we've seen in several examples, the eigenvalues appear as a sequence of separated values, right? So this is what I meant by discrete, nothing between them. In this case, we'll look at an example where the spectrum is continuous. So there's a whole continuous spectrum of eigenvalues for this particular problem here. So we'll take minus y double prime equal to lambda y. This is for x positive, and we'll require y of 0 to be 0, and then our other requirement, so we're just going to take y to be a bounded function. Okay, so let's see. So if we look at this equation, we've got y double prime plus lambda y is equal to 0. And so we have the usual three cases for y. Y can be, and then we've got something with Koch and Stinch, and that's going to be unbounded, no matter what we do there. Then we've got, it could be something like a plus bx, and then the boundary condition of being equal to 0 at 0 says that a is equal to 0, so it would just be a linear function, but that can't be bounded as well, so that was also out of the running. And so the last thing is the opportunity, or the only opportunity remaining, is for sine and cosine. So we've got a positive spectrum, and we've got y is going to look like a cosine x root lambda plus b sine x root lambda. And then let's look at our boundary conditions. So if 0 is y of 0, then we've got a times 1 plus b times 0. So a is 0, and we're looking at some sine function like this. And then our other requirement is that it be bounded, but that doesn't really throw anything out. This is always bounded. I mean, it threw out the case of negative or 0 in the spectrum, but it doesn't help us pin down anything more about this one in terms of what the possible values for lambda are going to be. And so the way to think about this is that in the standard case, when you're looking for the eigenvalues, think of it as sort of a problem where you have to line things up just right. Yeah. So I'm dropping this picture here because this is a picture of the kind of eigenfunctions that you get when you have requirements of y of 0 equal to y prime of 0 equal to 0 and y of 1 equal to 0. And so what I want you to do is envision yourself as living down here on the x-axis at 0, and you're, well, actually here, you know what? You're living up here, and you're like shooting a cannon, and you want to hit exactly this target right here, yeah? And so it needs to be the case that no matter how many times your ball bounces, okay, I realize this is not a physically realistic picture. You want it to be the case that so you're shooting some kind of a ray, and it has to be lined up so that it exactly, no matter how many times it wobbles, it comes right back exactly through this point right here. That's the requirement. And So in this case, when we're just looking at bounded solutions on the entire positive real line, there's no real requirement here. I can move this target any amount backward or forward, and things are still going to be fine. So, long story short, what do we get for eigenvalues? Well, anything. So it just needs to be a positive number. So if we put alpha equal to square root of lambda, then alpha's in the spectrum of our operator here. Let's just call it L, I guess. If and only if alpha is positive. So any positive number will work. Okay, so now if f is piecewise continuous, and absolutely integrable, so if its tails die off fast enough for this integral to converge, piecewise continuous is enough for it to be defined, at least formally. Whether or not the limit exists as we go out to infinity, that's another question. Then we can define the Fourier sine transform. So we looked at the Fourier transform and the Fourier series and the Fourier sine series and Fourier cosine series. So this is the integral analog of the sine series. And so f is going to be the Fourier sine transform of little f. And it's defined by f of alpha is the integral from 0 to infinity fx sine alpha x dx. Okay, so then our function f can be expanded not as a sum but as an integral f alpha sine alpha x dx, directly analogous. So here these sine alpha x functions are acting as our generalized eigenfunctions.